In this video, we discuss hyperbolic functions and their derivatives. These are functions that you may have never seen before, but they're just combinations of exponential functions. Here's our notation. That is y equals the hyperbolic sine of x. And it's actually defined as 1/2 of e to the x minus e to the negative x. So we can graph this relatively simply. And then think about limits of this function as x goes to positive and negative infinity. Limit as x goes to infinity of hyperbolic sine of x is the same as the limit as x goes to infinity of this function. And as x goes to infinity, e to the negative x goes to 0. E to a really large negative power is a really small positive number. Because remember, our e to the x function looks like this. There's y equals e to the x. As x goes to infinity, e to the x goes to infinity. As x goes to negative infinity, the y values approach 0. So this guy approaches 0. And then the resulting hyperbolic sine function gets very, very close to this 1/2 e to the x function. And as x goes to infinity, that function goes to infinity. So the limit is infinite, but it's almost as if we have an asymptote. And that asymptote is y equals 1/2 e to the x. We don't tend to use the word asymptote for functions that are not linear, but it's very similar to that, because we're going to have the hyperbolic sine function as x gets very large. It's just going to be this function minus a tiny, tiny positive number. So the hyperbolic sine function is actually slightly below this line as x goes to infinity. And similarly, as x goes to negative infinity, the hyperbolic sine is just this function. This will be e to a large negative power if x is going to negative infinity. So x is a very large negative number. So this guy is going to go to 0. And then we're going to have something that is approaching, well, this is going to be a negative times a negative, which is going to be a positive number. So we'll have e to a very large positive power times a negative 1/2. So this is going to be something that's going infinity times a negative 1/2. So the whole thing is going to go to negative infinity. So it looks like that. The hyperbolic sine function will approach negative infinity as x goes to negative infinity, but it approaches negative infinity in a very specific way. It's always going to be slightly greater than this negative 1/2 e to the negative x. E to the negative x just looks like a reflection of e to the x. It looks like that. And of course, when x is 0, e to the 0 is 1. Any number to the 0 power is 1. So when we multiply by negative 1/2, or multiply by positive 1/2, we get a 1/2 as our intercept there. And when we multiply by negative 1/2, we're going to have a negative 1/2 as our intercept there. So we're going to take this function and we multiply it by negative 1/2. So that's going to flip it. It's going to reflect it across the x-axis. And it's going to make it half as tall. So what we're going to see is a graph that looks something like this. This is y equals negative 1/2 e to the negative x. The hyperbolic sine function gets very close to both of those curves. And then a couple of other things. The hyperbolic sine of 0 is 1/2 e to the 0 minus e to the opposite of 0. That's 1 minus 1, which is 0. So the hyperbolic sine of 0 is equal to 0, which is just like the sine of 0. So it sort of reminds us of the sine function in that way. But it's very different from the sine function in the sense that it doesn't repeat itself. It's just this one function that approaches these exponential functions. If we want to take the derivative of the hyperbolic sine function, it's actually very easy to do. We just take their derivative of the definition, which is it's just defined in terms of those exponential functions. So we have a 1/2 times a function, so we can factor that out. Then we multiply by the derivative of the exponential. Derivative of e to the x is e to the x. Bring the negative down. And then the derivative of e to some power requires the chain rule. Here's our inside function. And we need the chain rule again because we don't just have an x inside, we've got a negative x inside, so we've got to do something else. The derivative of e to some power is e to that power times the derivative of the inside. And we all know that the derivative of a constant times x is just a constant, in this case, -1. So we get 1/2 times e to the x, and then a negative times a negative is a positive. We get that. And that's actually the definition of what's called the hyperbolic cosine function. So the derivative of the hyperbolic sine function is the hyperbolic cosine function. Just like the derivative of sine is cosine, the derivative of the hyperbolic sine is the hyperbolic cosine. So that's our hyperbolic cosine function. Look at the limits as x goes to positive and negative infinity for the hyperbolic cosine. As x goes to positive infinity, this is e to a large negative power. And so the function is going to go to 0. We can tell graphically by looking at this as x goes to positive infinity for e to the x, the y values go to 0. As x goes to negative infinity, or as x goes to positive infinity for e to the negative x, the y's go to 0. As x goes to negative infinity for e to the positive x, the y's go to 0. Or if you want to think about it just numerically, if you had e to the -10, that's 1 over e to the 10. That's 1 over a very large number, which is a very small number, which is why these guys are going to 0. So this guy is going to 0, and then this function is approaching infinity. So we get a limit of infinity, but again, it's almost like an asymptote. The hyperbolic cosine is approaching this function 1/2 e to the x. And it's always slightly more than that value. It's that 1/2 e to the x plus this tiny positive number that we're adding, and we get infinity. So our hyperbolic cosine function is going to be above that line 1/2 e to the x. Now, as x goes to negative infinity, we have basically the same pattern. We just have to think about what happens when when x is very large and negative. E to a large negative power is a very small number, so that's going to go to 0. And if x is a large negative number, we multiply by a negative times a negative is a positive. So we're going to have e to a large positive power, so that's going to go to infinity, multiply by 1/2, and we still get infinity. So the hyperbolic cosine is going to infinity as x goes to negative infinity, goes to infinity on either side. But again, it's going to be slightly more than that. The y values on the graph of y equals 1/2 e to the -x. 1/2 e to the -x looks like 1/2 e to the x, but it's just reflected across the y-axis. So it's going to look like this. And then if we evaluate this at x equals 0, got 1/2 e to the 0 plus e to the opposite of 0. That's just 1 plus 1, which is 2. 2 times 1/2 is 1. So the hyperbolic cosine of 0 is 1, just like the cosine of 0 is 1. So it makes it really easy to remember. So this one is y equals hyperbolic cosine of x. And this one is y equals hyperbolic sine of x. And the derivative of hyperbolic sine is hyperbolic cosine. Let's take the derivative of hyperbolic cosine. Again, just using the definition of hyperbolic cosine. Get 1/2 times the derivative of e to the x, which is e to the x, plus the derivative of e to the -x, which requires the chain rule. That's our inside function. The derivative of e to some power is e to that power times the derivative of the inside. And the derivative of a constant times x is just our constant. In this case, that constant is -1. So we get 1/2 e to the x minus e to the -x. And that is the hyperbolic sine of x. So the derivative of hyperbolic sine is hyperbolic cosine and vice versa. So these guys are the slopes of each other. And you might be thinking that function is the slope of that one. Well, yeah. And it turns out that this function is the slope of this one, which is kind of cool. Let's look at the graphs of both of those on Desmos and then look at some of the function values for the derivatives and show that the function values for the derivatives are equal to the slopes of the tangent lines. And they're basically just, this one gives you the slope of that one and vice versa.